Hello everyone, I hope you can hear me well. First of all, thank you all for joining our today's webinar. Let me just first introduce myself. So my name is Biljana Sovil and I'm sales manager at Exxon Power Electronics. I will be your host today, together with two of my colleagues, Dr. Srđan Sredić and Dr. Pavel Purgat, who will be our presenters today. So let me just give you a little bit of information on what is planned for today and how the webinar is organized. So for each of these presentation is planned around 20 minutes, and at the end there will be some time for questions and discussion. I would like to encourage everyone to write their questions in the Q&A section of this meeting. So next to chat you can find the Q&A section. So feel free to write your questions during the presentation and after the presentation, and at the end we will have some time to discuss these questions and to answer them. As you can see, webinar is recorded and you will receive the recording of this webinar after. Our today's topic is Introduction to Power Hardware in the Loop Testing with Real-World Use Cases. Our first presenter will be Dr. Srđan Sredić, and his presentation is on topic on unveiling the power of power hardware in the loop. Srđan is head of R&D department in Exxon Power Electronics, and he received his master, bachelor, and PhD degree in electrical engineering from the University of Belgrade in Serbia. And after that, he was with Department of Power Engineering at University of Belgrade, where he served as a teaching assistant and assistant professor. From 2015 to 2019, he was with North Carolina State University as a research assistant professor. His research interests include power hardware in the loop system and silicon carbide-based medium voltage and low voltage power converters. Our second presenter will be Dr. Pavel Purgat, and he will be presenting real-world use cases. Pavel earned his master and PhD degree in electrical engineering from Delft University of Technology, and he has been with Exxon Power Electronics, originally working with R&D team, and now as a part of a sales team. His research interests include power electronics application in power distribution, grid edge applications, and direct current system. With this, I think we are ready to go. I would like once more to remind you and encourage to ask questions, and I hope that you are going to enjoy our webinar. So Srđan, the floor is yours. Feel free to share your presentation. Thank you.
Thanks, Biljana. Thanks for the introduction, and thank you everyone for joining our webinar. Let me now share my presentation first. I hope you can all see it. Just a second.
Yes.
Okay. And the only thing left is to enable pointers so that we can kind of be able to focus more on certain topics. So, as Biljana already mentioned, the topic of this short presentation will be unveiling the power of Power Hill. I hope you can hear me.
Yes, everything looks great.
Okay, so basically, we would go through some very basics of the Power Hill, and also we would discuss a little bit about some simple guidance on how do you select and define your Power Hill system for your specific application. So let's get started. So the first thing that we need to figure out is like what is the purpose of Power Hill simulations and why do we use it for? So basically, the P-Hill simulations is there to facilitate the closed loop interactions between different components of different systems without having the need to create the entire system in the real world. The question is also like when to do Power Hill simulations, and the simple answer is as soon as possible, which means that basically, depending on if you are simulating the new system or you want to simulate the upgraded system that you have already developed, then the simulation should start as soon as hardware is available of such prototypes, or as soon as you can start with the simulations of the new systems. Another thing is like also that is also good to know is that the P-Hill simulations are not intended to replace the testing of the real system, unless the testing of the real system is really impractical due to different facts that can be like cost, risk, or schedule, or something like that. With that, we would also need to kind of define a little bit some basic terminology of the hill and power hill. This part is not going to be super interesting, but we need to go through this so that we can establish the basis pretty much. So basically, as I already mentioned, the hardware in the loop is a technique that allows closed loop interaction between the hardware of the interest and the model of the interest. So we already see that there are like two different parts of the entire system, which is hardware of interest and model of interest. The power hill is the type of the hardware in the loop where the hardware of the interest interacts with the model over the interfaces, while so-called natural coupling over those interfaces is preserved. What does that mean? In our specific case, electrical engineering, that in the simplest terms means that the instantaneous power at the power interfaces needs to be preserved. So power hill enables actually preservation of those of the instantaneous power at the interface point. Unlike that, unlike power hill, controller hill does not enable preservation of the natural coupling, meaning that the instantaneous power is not conserved at the interface. So that's pretty much the main difference between controller hill and power hill. This is how typical system of interest or power hill setup looks like. This is like a block diagram, and you can see here that we have the P-Hill software and P-Hill hardware, and in between we have P-Hill interface. Hardware of interest is part of the hardware, and the model of interest is pretty much within the P-Hill software. Both of these groups have their own control structures, P-Hill control structures, and both of those P-Hill control structures are getting their input from the interface algorithms. And control structures pretty much provide the kind of set points for the or interface to the exact model of interest and to the hardware of interest on the other side. An important part for us here is the power amplifier, which has certain characteristics, and due to the limitations of the power amplifier, it can affect the simulation, because the power amplifier typically has limited bandwidth, limited accuracy. So that's one of the things that need to be taken into account when power hill systems are developed, meaning the system of interest needs to, model of interest first needs to take into account all instabilities of the system. So if the system has certain instabilities, those should be preserved by the model of interest. Another thing that needs to be taken into account is, as I already mentioned, those imperfections or limitations of the power amplifiers. Those need to be taken into account, and very well known to the people that are using those power amplifiers. Together with that, if the power amplifiers, due to their limitations, can cause potentially some instabilities during the simulation, those should be known and taken into account, sometimes even potentially avoided. Like if there is like certain frequency range that we know that can have stability problems, that can be avoided if possible during the simulation process. Basically, what needs to be done, like before the simulation can even start, is there is a certain like checklist that can be used in order to establish the proper architecture of your power hill simulation. So basically, the first thing that needs to be done is you need to be able to determine which part of your system actually exists in the hardware, and which part exists as the model. That's even though it seems relatively simple and also like trivial, that is a very important task to begin with. And then, as I already mentioned, the interfaces between the hardware emitters and model emitters need to be chosen in a very careful way, and they should minimize their effects on the entire simulation should be minimized as much as possible. Also, of course, those effects need to be characterized so that we know where exactly you can expect some difficulties during the simulation. Of course, it's very, very important to be able to execute your model of interest in the real time, for which we typically use real-time simulators. And it's very important to choose the adequate time step of the simulations. Of course, that should be done synchronously. And another thing is that all those imperfections of the amplifiers themselves, of the measurement systems, should be taken into account. So now all this sounds nice and like pretty, but it's pretty much still very theoretical. So the question is, okay, what do I do with this? Like, how do I proceed? Like, how do I select my power hardware in loop system for my application? So we will try to provide several kind of simple guidelines for that. And for that, we can use this simplified model of our entire system where we can have an external real-time simulator with some control algorithm that is executed here. You can see here we have PI controller. Then we have power amplifier, which is very simplified, and it's pretty much represented as a first order system. And we have some transport delays, which are pretty much modeling the delay for the set point from the real-time simulator to the amplifier, and also the delay of the measurement signal from the measurement system back to the real-time simulator. So we would use this approach to kind of try to figure out how to select the different components of our power hardware loop setup so that we can have a meaningful and successful simulations. So the first thing to do here is to define a bandwidth of the model of interest. And this is pretty much one of the very critical points, which is very often not done properly, and which causes the problems later on during the simulation process and modeling. So basically, what is the model of interest bandwidth? That's pretty much the highest frequency that should be controlled in the closed loop in the system of interest. And then the question is how to select that, how to know that. So one important thing is that it's not the fundamental frequency of the system. And here are a few examples of how you can select that. For example, in the AC applications, that frequency is the frequency of the highest order harmonic that should be represented by the model. If you are doing impedance measurement, then that's the highest perturbation frequency to be tested. For electric machines, that's the highest frequency of the back EMF, or the highest frequency of the torque, or the highest frequency of the current ripple. So basically, you are aiming for the highest frequency that is of interest in your particular case. Once we know that, once we know the model bandwidth, we also need to define the quality of the signal that we would like to have at the bandwidth model bandwidth frequency. That's important because that would determine pretty much the accuracy of your simulation. So as you can see here, you can have the set points at different granularity here, and it's better if you can have more set points during the one period of the signal of interest at the bandwidth model frequency. So basically, in this case, you can see that if we have 10 samples here, that the representation of the analog signal is the blue. This one is the red one is with the 10 samples. It's very, very poor. It's much better if you, for example, have 25 samples per second. So for this kind of evaluation, we would assume that we are going with 25 set points per period of the corresponding signal. You can also choose 50 or more, but 25 can be a good measure. So once we have defined the output quality at F model max, then we need to determine the model cycle time. And that is done in a very simple way by just using the taking into account that we want to have at least 25 set points per corresponding that correspond to the model F model max. And in that case, this would be the equation that you can use, and this can give you the calculating model cycle time. Once you have the model cycle time, you need to determine what should be the real-time simulator cycle time, because your real-time simulator need to be able to send those set points and to process the measurement values during that cycle time. So basically, the very simple way of doing that, of estimating the real-time simulator cycle time, is to make it lower or equal to the model cycle time. That in that way, your real-time simulator will be able to execute the model with the required model cycle time. Now that you know the cycle time for the real-time simulator, the question is, how do you select the actual real-time simulators? And also the question is, what's out there, what's available? So typically there are two kind of technologies for the real-time simulators. So one is like CPU-based, and the other one is FPGA-based real-time simulators. So in this table, pretty much this is a short overview of the main properties of these two approaches, or these two simulators. So you can clearly see here that the CPU-based simulators are a little bit kind of slower because they have a higher cycle time. FPGA-based simulators are faster, but then again, handling of these CPU-based simulators is easier because the model accumulation is faster. You typically do not need to have any coding experience. Code generation is typically automated, and you can use simulation languages like MATLAB. On the other hand, of FPGA, some coding skills are required. Automation is not so good, and you also are lacking support with these simulation languages like MATLAB and Simulink. So then the question is, okay, what do I choose? Like, yeah, now I have my simulator cycle time, what do I choose? So basically, based on the technologies, and the technologies are evolving constantly, it's a kind of a good measure to select, to have like a kind of 4 microseconds as a point at which you would select whether you would go for CPU based on FPGA based. So if your cycle time is less than 4 microseconds, it would be a good idea to go to the FPGA based approach. And if it's higher, then you should consider CPU based approach. Once we know this, and of course there is an overlap between those two. Once we know this, then we need to determine what should be the properties of the amplifier so that you can actually simulate the things that you want to simulate, considering your model bandwidth. And based on the empirical data, it turns out that it's a good engineering practice to select the power amplifier bandwidth to be like 50% higher than the model bandwidth itself. And that's the kind of design guideline number 6. So selecting the amplifier bandwidth to be roughly 50% higher than the model bandwidth. Once we know that, we need to figure out the stability of the system. Like, we need to consider like, what would it take to make our system stable? And in order to assess the stability of the system, we can do that by checking the system open loop transfer function. If you remember, we are considering a system where the amplifiers are very simplified and represented by the first order system. So if we assume, for example, that the phase margin would be 60 degrees, which is kind of a good engineering practice, then that would mean that we would have a phase shift of 120 degrees. And translated to the open loop delay time, the open loop delay time can be calculated like this. And again, that open loop delay time consists of the delay of if you remember in the diagram, of the delay that is between the real-time simulator and the input of the amplifier, then the delay of the amplifier itself, and then the delay of the measurement system. So by having this open loop delay time, we know pretty much what would be the limitation of the amplifier. What do we need to achieve from the amplifier side? And based on all these guidelines, we can kind of get to this P-hill selection diagram, which is a very simplified version, but it's a good first step for you to estimate and to determine what exactly do you need for your specific applications. Of course, later on, you can replace the simple first order model of your amplifier with a more realistic model of the amplifier, but this can serve as a good starting point. So basically, let's say that we have a model with a bandwidth of 2 kilohertz. Now the question is, what is required? How do I determine all these values that are power amplifier bandwidth, model cycle time, and open loop delay time? We can get that relatively simply by just checking these cross sections with these lines, and then we can see here that for the model with the bandwidth of 2 kilohertz, we would need the amplifier bandwidth of 3 kilohertz. The open loop delay should be less than 167 microseconds, and the model cycle time should be around 20 microseconds. So that's the basic kind of first iteration for you to determine what exactly is needed in terms of power hardband loop system, so that you can successfully model and simulate your system of interest or your parts of your system in a specific application. What are the benefits of the P-hill? The simplest and the first thing that comes to our mind is that it can reduce the cost, because especially in the cost of very complex system testing system in P-hill can be much simpler and much cheaper than the testing of the entire system. Also, the risks with failures are reduced because edge conditions can be tested in much safer environment using P-hill than the real system. Also, what's important is that you can have the simultaneous development of different components of the same system. For example, you're developing electric machine for the EVs, electric machine in the inverter. So during the development, you can develop them in parallel, and you can actually simulate, for example, inverter with P-hill and use that to test the machine, or you can simulate the machine with P-hill and test the inverter against that P-hill that simulates the machine. Also, what's important is to be able to test different plant variations with the same setup. For example, you test inverters of different power levels, and in a typical case, you would need to have several motor generator groups of several different power levels. All that can be replaced by one P-hill device, which can just be then simply configured by changing parameters, which significantly simplifies that task and not just simplifies, but also reduces the cost. Also, one important thing is testing the fault modes, like failure modes, which typically are very, very impractical to test in the real systems. Where do we see the power hill, in terms of fidelity and flexibility? So basically, here we have some acronyms. This is computer simulations. This is control hill, this is power hill, and system test bed. You can see from this one, and also on the right-hand side, you can see how we see where these simulation kind of approaches fit best these technology readiness levels. So basically, pure simulations have the widest test coverage, but also the test fidelity is not that good because it's based on the models only, which have their own limitations. The second in line is controller hill, sorry, which has a slightly lower test coverage, but it has a little bit better test fidelity because you are involving some real models, real controllers. The next one, which we believe is a quantum leap in the simulation technology, is p-Hill, because of those of the preservation of the natural coupling. So basically, that significantly increases the test fidelity, but also it also a little bit decreases the test coverage. And also what needs to be taken into account are the limitations of the system itself, primarily limitations of the power amplifiers in terms of bandwidth, accuracy, etc. And the last thing here is system testbed. System testbed provides the best test fidelity, but the bad side of the system testbed is that it typically developed for only like a few very distinct applications. So it cannot be widely used for different applications because it's built for a specific purpose. How do we see the p-Hill applications when it comes to the frequency for the bandwidth? So this is just an estimate based on our experience so far for the bandwidth and the range. So the main applications are grid-related applications, then wind and solar, powertrain applications, various applications for power converters, and also we have low power and automotive and aerospace applications, which are a little bit specific because they require relatively low powers but higher bandwidth. And that would be all from my side for now. So please prepare your questions. We would try to answer as many as possible. And as Biljana mentioned, at the end of our session, we will answer all the questions and send you the answers. Thank you.
Okay, thank you, Sergeant, so much. I think it was a really interesting presentation. We will give some time people to digest this presentation while Pavel is also presenting. So Pavel, yeah, please feel free to share your screen and start your presentation.
Thank you very much. Thank you for the introduction, and thank you everybody for joining us today and also staying for the second part of this webinar. In the second part, we will use some use cases. I have prepared use cases from 3 different areas. The first area is from the small signal stability. So we will start with the small signal stability, measuring converter impedance and admittance, which was co-developed by Extend, one of our customers. And then we will move to slightly large signal scenarios, and that's testing and validation of grid supporting converters. And in the last part, we will look at how power hardware in the loop can be used when a certain piece of hardware is not yet available in your laboratory. However, you would need it, and you would need it for testing. So you can think about a scenario where you have a machine, but not a converter to test it, or other way around. You have the converter, but not the machine. How can I test the converter then? Since all 3 scenarios are from power systems, I would like to bring your attention to some of the basics about the dynamics that we see in modern power systems and how they are different from the situation from, let's say, 30 years ago. First of all, we can look at the time constants of different phenomena that we can observe in the grid. In the past, when the grid was mostly dominated by large synchronous generators or similar devices, the time constants of the phenomena that we observed were at fastest in millisecond range. So these were electromechanical phenomena. However, as more sources and loads in the system are interfaced via power electronics converters, naturally also the switching surges or their controllers are showing in the grid. So what this leads to, it means that when we are evaluating the power system stability, looking at the traditional frequency, angle, and the voltage is no longer enough. We have a new group of stability phenomena, and that's electromagnetic stability, very often referred to also as converter-driven or harmonic stability. Now, electromagnetic stability as such is a small signal phenomena. This means that it's local by nature, and to evaluate it, we need two things. First of all, we need to evaluate it at the right operating point. And second of all, we need to evaluate the reaction of the system to the small signal perturbation. So what we need from our measurement device is to impose the operating point on the device of interest and perturb it with a small signal in a sufficient frequency range. Now, what are the typical devices that we would measure the impedance or admittance of? So when we look at the converters in a power electronic or in the power system, we can roughly divide them in two groups. Either they are grid following, which is a technology that's more frequently used today. That means that they are synchronizing on an existing voltage, frequency, phase angle, and phase sequence. And to that end, they use PLL, phase log loop, or a similar mechanism, however, PLL being the most used one. And another distinct feature of the current grid following converters is the current controller. That means that these converters are behaving as current sources or current loads. For us, when we want to evaluate their stability at the point of common coupling with the grid, it means we need to measure the admittance of these converters. On the other side, we have the grid forming converters. Now, grid forming converters were not used as much in the past as the grid was formed by the synchronous generators. However, today, for microgrids or even for bigger grids, this is a technology that can be described as emerging, and there is a lot of traction behind it. What is different is that we have no longer a PLL, logically so, because we are imposing the voltage, and we have a voltage controller. So the converter behaves as a as a voltage source or a voltage load if there is a battery, let's say, on the other end. For the evaluation of small signal stability, it means we need to measure impedance. So for the equipment that we will need, it means it needs to be able to impose the operating point, impose the perturbation, and it needs to impose the perturbation both in the voltage and in the current. So we need both sufficient current and voltage bandwidth. As I mentioned, together with one of our customers, we have developed a method that uses external amplifiers to measure impedance or admittance of a converter or a power system at the point of common coupling. What we need are the power amplifiers that are both imposing the operating point, so the nominal voltage and nominal currents, and are able to modulate a perturbation on the main signal. There needs to be a single control point. Why we need a single control point is that then we don't need a synchronization signal between the main signal and the perturbation signal. Moreover, when we have a single point for control, we can measure the voltages and reflected currents, or other way around, currents and reflected voltages, at the output of the power amplifier, and then save them at the computer for the later analysis. The waveforms and the perturbation signals can be programmed using a scripting tool that's also part of the Exton family products. The measurement procedure itself is relatively simple. We start with an operating point of interest. We are perturbating it from very low frequency to the very high frequency, or to the frequency that we need. And the sequence of frequencies that we are interested in can change. What we need to keep in mind is the amplitude of the perturbation, because if it's too small, the signal will be lost in the noise. Also, if the duration of the perturbation is too short, the device that we are testing might be unstable, and such a measurement would be not valid for the calculating of impedance. And then the impedance itself is calculated using the fast Fourier transform for both voltage and current, and then doing the necessary arithmetics. To demonstrate this method, we have used our smallest unit, CSU 100, which is a 100 kilowatt unit that as a standard comes with 4 power amplifiers on the output. So we have a phase modular approach, 1 power amplifier per phase. One advantage of this approach is, of course, the versatility of such a power amplifier. But also, the signals are extremely clean. The THD at 50 Hertz is only 0.04% at no load. Such unit can be scaled with power and also voltage. And what is important for this part of the presentation is the bandwidth. So it can go up to 30 kilohertz for measuring of impedance or admittance. Now we are looking at the actual test setup that we use to demonstrate the methodology. We have two groups of power amplifiers. Normally, this is done so that we can circulate the power on the common DC bus. Now, the advantage of circulating power over the DC bus is quite clear. The grid that is supplying the power only needs to cover the losses in the transformer, the active front end, and the power amplifiers. However, here we wanted to measure the admittance of one of the groups that is current controlled and the impedance of the other group that's voltage controlled. In the experiment, the group 1 was voltage controlled, acting as a grid forming converter, while the group 2 was running with a PLL and was synchronizing on the voltage. The group 1, when we need to measure the admittance of the current control device, is injecting perturbation to the voltage. And then the voltage and currents are measured at the point of common conflict. On the opposite end, when we are measuring the impedance of the voltage source converter, we are injecting perturbation to the current and then measuring again the voltages and the currents. Here we are already looking at the results of the measured admittance of our grid following converter, or essentially our amplifiers running in the current mode. What is interesting to notice, of course, there is a peak at 50 Hertz. This was our operating point. You can see we did it for different currents as well, so there is some difference. But also it's important to observe that we are able to measure both the magnitude and the phase at a very high frequency. So we have sufficient power also for the higher frequencies in our perturbation to voltage. Similarly, when we would measure impedance of a grid forming converter, we need to have sufficiently strong perturbation in the current. And you can see it here. We were able to measure both the magnitude and the impedance all the way to 30 kilohertz. When you would then want to use this data to evaluate the stability, you would take the impedance and then look at the ratio of your converter impedance with the grid impedance, and if it satisfies the Nyquist criterion, of course it is stable or maybe marginally stable, etc. However, now to move on to the large signal phenomena, I would like to invite you to a little trip to Germany and introduce you to a laboratory at Karlsruhe Institute of Technology. The researchers at KIT have at their disposal a 1 megawatt ampere power hardware in the loop setup supplied by extant power electronics, and then two smaller P-hill setups by different manufacturers. What's even more interesting, they have quite a variety of energy storage technologies at their disposal and that can be used for research. One of them is 120 kilowatt high-speed flywheel. That is the technology we will look at today. But there is also a 500 kilowatt supercapacitor energy storage, a gas turbine, and a liquid hydrogen energy plant. The unit that will be the hero of the following story is a 200 kilowatt unit. Now, this unit is almost identical to the previous unit when we are talking about the bandwidth, however, and the scalability, except it can, of course, go to megawatt region. However, it has 6 amplifiers, which means that when we are using it in a 3-phase operation, we have 2 amplifiers per phase, thus doubling the output power. Now, for those of you who, like me, are power electronics engineers, there is a small refresher on the indicators of frequency stability. Frequency stability in a power system is normally evaluated by the nadir, which is the lowest point of the frequency drop during the disturbance, and the Rokov, which is quite a clear acronym for rate of change of frequency. When we look how this is then dealt with in a power system, we have 2 types of control, the primary control and the secondary control. During the dip, we hit the nadir, and then the primary control recovers and bounces back the frequency slightly. It stabilizes before the secondary control can take over and then go back with the frequency to the nominal operating point. What we'll be looking at today is the primary control, and namely, if we can use the flywheel as a primary control device. Now, in case you are wondering why flywheel, one of the big advantages of flywheel is quite high power density plus fast response, and it can hold the response for several seconds. So it is quite a natural application. Now, how can we test that? And more importantly, demonstrate that this is possible. Ideally, we would go to a microgrid or a real grid, connect the flywheel, and then do the tests. However, no DSO will be particularly happy when we introduce a fault and a frequency deviation just to check our novel algorithm. A bit more easier method would be to build a model of the microgrid and then deploy it on a real-time device. So this is exactly what the researchers at KIT did. They built a model of a Seagray-based microgrid that contains several nodes, a PV plant, and a combined heat plant as well. And this is deployed on a real-time platform. The real-time platform is connected via optic fiber communication to the external power amplifiers. So this is a high-speed communication link over which the set points for the power amplifiers are sent. The power amplifiers are connected via power connections to the flywheel structure, as we can see here. And then we have a measurement to close back the loop. This should remind you a little bit the slide from the previous presentation when we had the P-hill structure. This is our system of interest. This is the model of interest, and this would be the hardware of interest with the interface here. The interface that was used was the ideal transformer model when we are sending voltage set points and receiving back the currents. The scenario at which we were looking at is an islanding scenario. That means what happens when the microgrid disconnects from the main grid, and can the flywheel reduce the nadir during this procedure? Now we are looking at the results. So this is a bit of an in medias res. The black curve is the base scenario without any support from the flywheel. And the red one shows the proposed novel algorithm for the flywheel control. As you can see, compared to the base scenario, the lowest frequency point is reduced by almost 40%, and the rock-off is slowed down by 25%. What is also interesting is to observe a difference between the controllers. So thanks to the fact that we can deploy the controllers on the real-time device, we can relatively easily compare different controllers, and that we can see then here that, for example, the proposed controller achieves much faster ramp up for the flywheel, and thanks to that outperforms the other state-of-the-art controllers. Now moving to the last example, and that's coming again from Germany, but this time from Munich, and from a Center for Combined Smart Energy Systems. The researchers at COSES have at their availability a 200 kilowatt P-hill setup. However, it is very special as it has 7 independent groups of amplifiers, and we will see in the next slide how they can be used. A flexible grid, so a grid which connections, topology, and the distance between the poles can be changed, and several technologies from heat sector, such as configurable heat grid, air source heat pump, house heating system, and a combined heat plant as well. The grid itself consists of 2 microgrids, as you can see here, each supplied by a separate transformer that can be connected but doesn't need to be. So they can be used completely separately, but also if you would like to test deployment of optimal power flow or similar things and how the energy would be shared between the 2 microgrids, this is also possible. What is also possible is to change the lengths of the cable between the points. Now, the advantages of that are, of course, clear, for example, for protection testing. Moreover, there are houses or representation of single or multiple family houses, which we can see here 1, 2, 3, up to 7. Each house can be represented by one group of amplifiers. So there are 4 amplifiers, 1 amplifier per phase. Moreover, they can be connected to a car charger, PV with a battery, a heat sector coupling, or plugs for appliances. So they can really quite well represent a realistic household with its consumption. However, what's most interesting, at this research center, the researchers have available a air source heat pump. Now, what they realized is that most labs don't have air source heat pumps at their disposal, but they might be interested in testing these devices and how they react with the electric grid. For that, they have developed a relatively universal model that with several parameters, especially in the thermal domain, can represent different types of air source heat pumps. Now, if you are wondering why tinkering with the mechanical model, the idea is to capture the nonlinearity, and the nonlinearities typically come from the mechanical load transients, which are predominantly determined by the pressure in the evaporator and the condenser. And the two models, so the thermal and the power model, are then linked by the power and the rotating speed of the machine. If you would want to use that kind of a model for a P-Hill setup, the model itself is again deployed on a real-time platform. This time is split in two. So the slower thermal subsystem is simulated on one core with only 200 Hertz step. And the faster electrical subsystem is simulated on a faster CPU with 10 kilohertz time step. Again, we would use an ideal transformer model, but this time the amplifier needs to behave as a current source, so it needs to have a sufficient current control bandwidth. And on the output of the amplifiers, we are measuring the output voltages, sending them back to the model, and sending the current set points back to the amplifier. When we look at the results and compare the power amplifier output to that of an actual air source heat pump, we would see quite a good match even for highly nonlinear current. This, as I said, is especially owing to the fact that the power amplifiers have a sufficient bandwidth also for the current control, and they can match also the higher order harmonics very well. Yes, there is admittedly a steady state error. However, this can be mitigated by further improving the integral gain, essentially by tuning the PI gain, which is also possible. And with this, I would like to thank you. So I wanted to show you how power hardware in the loop, first of all, can be used to study a system stability, especially modern power systems such as data centers, how power hardware in the loop can capture nonlinear behavior of a power system or a power converter, and also how you can, with the benefit, use it for concurrent testing. That can mean either testing different algorithms or different scenarios very rapidly, or if part of hardware is not yet available for whatever reason, if you have a model, you can represent that part of the hardware using the power hardware in the loop setup. Thank you very much. And now we are ready to answer the questions.
Okay, thank you, Pavel, so much. It was a really nice presentation. A lot of questions happened in meantime while you have been presenting, so I think that this topic is quite interesting. So let us see with what we could start. There was a question, what are the capabilities of power hardware in the loop for end-of-life estimation of power electronics devices, and how complex is it to consider data-driven models or physics-informed models for testing?
Okay, so maybe I can take that one. So, I mean, that's a very open question. So in order to give you any more information, we would need a little bit more specific, like details, like what exactly is needed, like what are the power levels, current levels, voltage levels, what kind of dynamics do you need, what needs to be tested and simulated. Otherwise, it's very difficult to answer it. I mean, in general, as long as the model requirements are within the bandwidth of our system, and also as long as the current voltage and power requirements are within the limitations of our system, it can be done in principle. So you would also need to be able to, depending on the model complexity, you would need to be able to simulate that whatever you want to check in any of the using any of the real-time simulators, and we are compatible. Our amplifiers are compatible with all pretty much major manufacturers of the real-time simulators. So in essence, that's the best answer that I can give. For the more specific answer, we need more details.
Okay, and we have one hand raised, but just before I ask the person, there was a question, just if you can come back to your slide 15, Srijan. And there was a question regarding time and frequency parameters. So if you can just quickly explain once more this slide.
Let me share it again. So basically, oh, not that one, not that one. Sorry, just give me a second. Not this one, this one here. So basically what we have here on the x-axis, that's the model bandwidth. So that is the highest frequency that you want to simulate with the real-time simulator or with this P-Hill system. So that's the frequency of the system that you want to simulate, the plant. These characteristics here, the blue one is the required power amplifier bandwidth. So in order to simulate successfully the system, which model has 2 kilohertz bandwidth, you would need an amplifier with a bandwidth of 3 kilohertz. The model cycle time, that's the thing that you need to know in order to be able to select your real-time simulator. That's 20 microseconds. So in this case, you would probably be able to use some CPU-based simulators. And then the loop delay is 167 microseconds. So your amplifier should be such that the total loop delay, or your system should be such that the total loop delay is less than 167 microseconds. So in that case, you can expect some meaningful results. Again, these considerations are developed based on the simple model of the amplifier, where the amplifier is pretty much treated as a first order system. So for any better estimate, you would need to use a model of your amplifier and your entire system that more closely represents your actual system. I hope this answers your question.
Okay, I also think that this clarified a little bit this question. So we have Siu Chen. He raised his hand, so maybe we can hear from him and see what questions he has. So please ask your question. Or maybe he changed his mind. Okay. There are also some other questions I see coming in the chat. So there is a question: are converters OEMs getting their converters characterized by impedance in order to supply to customer?
Well, maybe some. We have developed the method that I showed not with an OEM, however, with a company that needs to check if the cascaded systems in their application are stable. There is not that many details that we can provide on that, but more and more people are talking about impedance characterizations in the meeting. So this is not just in IEEE literature coming up as a topic. So it's a good guess that we will see more of it coming up in the future.
Okay, thank you, Pavel. Let me see. Is power hill capable of emulating a 2L inverter switching up to 5 kilohertz?
Srdjan,
I
your
was
mic.
just about to answer that one. So first, hi Milan. The question is simple. We cannot do that because like switching events have much higher contain much higher frequencies because like they have very fast slopes. So what we can simulate here, we can simulate anything that is up to 5 kilohertz. So we can produce 5 kilohertz sine wave at the output. So we were testing before some kind of switching converters like line frequency converters, like diode bridges and thyristor bridges, and we had some success with the diode bridges, but fast switching events we cannot simulate simply because the bandwidth is not high enough.
Two questions appearing. So I will just read a couple of them so you can choose which one are the most interesting, maybe for the most of the audience. What are the conditions for physical validation of mixture of GFL and GFM inverters? Then what is the current issue with P-Hill simulation are facing? Is it only stability and accuracy? For large system composed of modular converters, thousands of these with GFM's capabilities, P-Hill would be an acceptable solution, or the best would be a C-Hill simulation. Those are some three that I just found. Is it something that you can easily answer, or which ones you can cover in this short time?
Okay, so a lot of these are kind of like open questions. Maybe Pavel, you can take these regarding the converters. Large signal stability studies beneficial of real-time simulation, but P-Hill is a real-time simulation. So we use models that are executed on the real-time simulators, and we also provide we have power amplifiers so that we have power interface actually, and at the output we can provide the real power. For example, if you're simulating one grid and you want to check the status of one signal node in that grid, you can actually have our amplifiers simulating the state of that grid in that node, for example. So P-Hill is a real-time simulation. So how do you envision? Okay, these are a lot of open questions. So again, like whatever is within the bandwidth limits of the amplifiers and also the electrical limits of the like powers, currents and voltages, those things in principle can be simulated. Now it depends on the complexity of the model, if that is practically feasible or not, but in principle it can be done.
Yeah.
Okay. Thank you, Srdjan. I mean, there are a lot of open questions, and we are at this point over time that is planned for this webinar. I'm glad that I see this many questions because this just proves that this topic is interesting. I hope that you really enjoy this webinar, that you have learned something new. I would like to thank you all for participating, to thank my colleagues for such a nice presentation. We will for sure organize something similar soon. And yeah, until then, enjoy your time and hope to see you soon. Bye.
Yeah, thank you everyone. And
Bye-bye. Thanks
I just
everyone
would
for
like
joining.
to add, I will try to answer the questions for those of you who registered via email when I can. If I forget, please feel free to reach out to us. We are happy to talk about power hardware in the loop anytime. Thank you very much.
Thank you. See you. Bye.
Goodbye.